Значит, он пишет. Раз. Мы видим какой-то...
Спросить, кто слышит.
Атом никак... Окей, let's assume that is clear.
Ага, так. Еще 3 минуты, 2.
Обычная практика, когда какая-нибудь конференция или что-то в последнюю минуту.
В этом все еще с отпуска пришли. А он такой же, обычный. Такой. В смысле, на доске не показывает? Да. Ну да. Может, поэтому решили лучше. Ну, так, он подключен уже. Zoom все равно не видит.
Ну, вроде Zoom нас должен слышать. Я не знаю, какой звук. Раз.
Кто-то если появится, я думаю...
Ну, тут вроде как он показывает, что что-то первое.
Да. Ну, добавите вот теперь. Привет, наш.
Да?
И надо вот эту штуку.
Ну, какой звук хотим? А что они видят? Они видят экран или...
Вот сейчас все видят вот это.
И скрыть элемент управления
Да.
конференцией. Это высший пилотаж, то есть это можно свернуть, вы меня и так видите.
Можно еще, да.
Вот так, да, вот это.
Все. Теперь только нужно нажать на окно, чтобы он включился.
Да.
Я тогда представлю, если не управляешь.
Окей, я.
У нас есть еще, кажется, вот полминуты, можно подождать, чтобы как бы все могли включиться в Zoom.
Подожди. Миша, зайдет.
Миша,
Да? Или гайки закрутили?
Нет, это говорится...
Это мой, короче.
Okay, dear colleagues, it's a big pleasure and honor for me to present the first talk of this season, which will be given by Maxim Gorlach, head of his group of 10 people at ITMO University, which has a very broad and diverse range of research directions, including topological metamaterials, research for axions, but there will be much more, and recently also research into qubits, which Maxim will be talking about today. Maxim, will you prefer questions during the talk?
Yeah, please feel free to ask, because the audience is not very large, so I will be happy to take your questions just.
Okay, the stage is yours. You have approximately 1 hour.
Good. Many thanks, Anton, for the introduction, and many thanks to the team of Abrikosov Center for hosting me here for several weeks. It's really a pleasure for me to visit you during this summertime and have some discussions. So today I'm going to present our recent work devoted to broadly to the domain of quantum optimal control, quantum technologies. And we are studying the problem of time-optimal transfer of the quantum state in the array of qubits. And this was recently published just July of this year in Physical Review Letters. And of course, it's not done solely by me, but by a team of people. So I come from ITMO University, Department of Physics. I do believe most of you know a lot about us, so I don't have to introduce this center. It's a relatively big department, around 400 employed people, including students, and around 20 PIs, with a lot of interesting activities. Of course, I have no chance to introduce all of them, so I will just focus to the topics pursued by our group. So this is the photo, couple of my students. So actually, Andrei, who is the first author of this paper, already graduated and now continues his career in United Kingdom. So current technological capabilities allow people to fabricate arrays of coherently operating qubits with the numbers of qubits more than 100, several hundreds of qubits. There are different companies which compete in this domain. This is a very hot topic nowadays. But the real issue is not fabricating a lot of qubits. The real problem is controlling all of them and ensuring that all of them operate coherently. So this topic, controlling this large-scale quantum system, is investigated by such discipline as quantum optimal control. So if you have a system with just few degrees of freedom, let's say you have a rigid body, it has 6 degrees of freedom. So it's so easy to control it. So you rotate it, you move, you have full control. However, if you have system with multiple degrees of freedom, like a glass of water, its control becomes much more challenging. And those quantum systems, if you have n qubits, you have 2 to the power of n degrees of freedom, and the optimal control is notoriously challenging. So until recently, the optimal control for relatively simple systems could be computed, in some instances even analytically. However, there is an open problem of finding an optimal control of some large-scale system. So there are different platforms for implementing qubits. I had some experience with superconducting qubit architecture. So here I provide some characteristic numbers, and we continue collaboration with experimentalists. Actually, there is a nice experimental team just next doors to you in the adjacent building. They are working with very low temperatures, around tens of millikelvins. Those qubits which they have transition frequencies around few gigahertz, and they could control couplings in a very broad range. There are alternative platforms based on trapped ions, based on cold atoms. There is this paradigm of photonic quantum computing. So this is very active topic nowadays. So in our theoretical work, we study a specific system, an array of coupled qubits, and we assume that there are only couplings between the nearest neighbors. So this picture, that's from our 2021 paper, that's how those arrays of qubits look like in the superconducting architecture. So obviously, it's not so easy to make long-range couplings, but the short-range couplings are easily implemented as just additional capacitance between these crosses. So each qubit is this kind of cross, and the central element of this qubit is the so-called Josephson junction, which from the classical perspective could be viewed as a nonlinear inductance, but essentially provides this quantum ingredient of this system. Now, in our work, we study the following quite simple toy model. So we study a system with the Hamiltonian shown on this slide. We assume that all qubits are identical, so they have identical eigenfrequencies denoted as omega 0. And we have a flexible control of the couplings between the qubits denoted as JK. So each coupling could be controlled independently, and it describes the hopping of a particle of an excitation from qubit with the number k to the qubit with the number k plus 1. So if we are working with the array of length n, then there is n minus 1 control parameter, all couplings. And we are interested in transferring. So we launch our excitation in the first qubit of the array like this. So we have a wave function in the single particle, in the basis of single particle states like this. And then we assume that we have a full control of the couplings. All couplings are controlled independently. And we are asking a question. So how can you transfer this excitation to the rightmost position within the minimum possible time? if we are asking such sort of questions, minimizing some time, of course, there should be some constraint. If there are no constraints, then there is no minimum time. So you could do this instantly or somehow. So in our case, the constraint is imposed in this form. So like the overall magnitude of couplings is like resource which you could distribute, but you cannot have infinitely large coupling. So the sum of the squares here is constant. Given this constraint, we are raising a question. So what's the minimal possible time? And of course, we would like to get the final state of this form, so not something else, up to the phase. So the global phase is irrelevant.
Is it arbitrarily chosen constraint, or does it have a physical origin?
Well, constraint, I would say it's motivated by the simplicity of calculation. So you will see why this form of constraint is somehow simpler. I was presenting this talk in a couple of places, and in experimental situation, of course, you have not this kind of constraint, but rather an upper bound on the magnitude of couplings. In this case, you have to modify this calculation procedure a bit, but still the approach works. Please.
How do physically change, one can change these couplings in time?
Yeah, a good question. So in the superconducting architecture, they use so-called tunable couplers. Essentially, you have two qubits, you insert the third one between them, and then you are changing the frequency of this auxiliary qubit. And by changing the detuning, you control the coupling in the real time.
So this should be implemented from the beginning in the scheme of.
Yes. So when people talk about superconducting architecture and when they mean tunable couplings, all experimentalists understand that they have to use this scheme with auxiliary qubit with a tunable frequency. As far as I understand, nowadays it's kind of routinely done, so it's not science fiction anymore. It's more or less routinely done, available in Google chip, and even simpler people, like I had discussions with a couple of Chinese colleagues, they can readily do this stuff.
So actually, alternatively, you could think of a model where all couplings are fixed, but the frequencies are changed.
Yes, some of the frequencies. Yes, some of the frequencies of auxiliary qubits inserted here and here, they're changing, and this way you tune your system.
Could you also comment on this initial state and desired final state? Are you considering any state that is kind of superposition of two basis states of a qubit, or you wanted to have some specific value? Like
good. Important question. So overall, if we have n qubits, our Hilbert space has the dimension 2 to the power of n. However, this Hamiltonian conserves the number of particles, so it commutes with this operator sum over k and k. This means that the Hilbert space decomposes into the subspace of single particle excitations, two particle excitations, etc. We study single particle.
From Zoom.
Yes, so sorry, I'm answering just the previous question, Mikhail. Yeah, let me answer the previous one. So we study the domain of single particle excitations. Then you have a basis of n states, and then we can explicitly write our psi as a column vector with n entries. And we can write our Hamiltonian as traceless Hermitian n by n matrix. So, Alexey, did I address your question?
Not entirely. I still want to realize what is going on. So you have some input to the system. So you you initialize the first qubit in a specific state, which is not necessarily one of its basis states. No, it may be any state.
It just excited state of a qubit. Yeah, just excited.
By excited state, what do you mean? A superposition of 0 and 1?
No, just one. Just one.
So it's like a classical.
Yes. So in fact, you could talk about coupled mode theory for coupled resonators. Then you'll get more or less a similar picture. And then we want to, due to the coupling between the qubits, this excitation could be transferred somehow. And then at the end of the day, what you want to have is excited state of the last qubit in the array.
So in which sense they are qubits then? We transfer a classical state, these are classical bits?
Well, I'm studying the array of qubits, but you are certainly right that you could study like array of coupled oscillators. If you could initiate this sort of excitations here, let's say array of waveguides, similar physics should happen. So I'm not emphasizing that it's some quantum advantage or something.
So out of all out of the infinity of possible initial states of a qubit, we take one, which is this pool state,
yes,
one of two basis states, and we transfer it.
Yes,
And
absolutely. Yeah, that's what I'm solving. At the same time, I have to comment that the methodology is general, so I can, in principle, apply this to the superposition state. If we're interested somehow in the transfer of entangled state, etc., we can do this job as well. So the methodology is general. The only question is then we get the solution, how you interpret it, what kind of useful information you extract from there. Okay, good. I hope I clarified the problem setting at least. Mikhail, you had a question.
Yeah. So the sum of this hopping constants squared is a constant. That it's not infinity. So you assume from the beginning a finite system.
Yes, absolutely right.
Then I can imagine that in some case you have, for example, if they are just SSH model, but you two different constants, then you have topology you out of it.
Yes, sorry, the connection is not so good, but as I got your question,
yes. So I'm saying I'm asking
I think it's
about finite size effects.
That's a problem from our side, certainly. Yeah, but well, I get incomplete information. I have to interpret. Well, I guess Mikhail is saying that in case we realize the SSH.
Yeah, I can repeat the question.
Please, and sorry for this.
Yeah, I'm trying. Maybe I should put it in writing. I'm asking about finite size effects, the H states.
Well, you are certainly right that there could be H states in the lattice with constant couplings, but here we are dealing with a time varying case. So I could imagine the situation that initially you have SSH pattern of couplings, localized state at the left edge, and then you instantly, let's say, switch the pattern of couplings, and your eigenmode should appear now at the right edge. It appears that such instantaneous switching of couplings is non-optimal in terms of time. So the time of transfer grows exponentially with the size of the array. If we're just thinking about SSH and changing dimerization instantly, then you will have exponential scaling of the transfer time. So it's not so easy, really. So I hope I will have a chance to go to the next slide and then present the solution which we get. And another thing which I wanted to briefly mention here in this context. So you know that in the usual Schrödinger equation, there is no characteristic speed, no speed of light. It appears in Dirac equation. But if you are studying tight binding lattices, then this maximal speed appears. It's known as Lieb-Robinson bound, or it's also discussed in physics literature as the quantum speed limit. So if you want to transfer a quantum state and you have some constraints on your Hamiltonian, you could actually do this with a finite speed, not instantaneous. Now, before doing the detailed calculation and showing you the methodology, I should convince you first that the solution to the problem I outlined exists at all. And then there is a very simple strategy which allows you to transfer the excitation from left edge to the right. So let's look at this. You may follow the following strategy. First, you switch on the first coupling between the first and the second qubit, and you wait for some time until your excitation goes from the first qubit to the second one. It's actually pi over 2J. Very simple problem to solve, like simple exercise for the undergraduate student. Next, you switch off the first coupling and switch on the second one. And again, wait for some time when your excitation moves from the second to the third qubit. We repeat this procedure n-1 time, and then we get this time of the transfer for n qubits given by this formula. This receipt certainly gives you the fidelity equal to 1. However, as I will show you later, this strategy is not optimal. Interestingly enough, there is yet another approach how to transfer the excitation, which was published by some knowledgeable people 20 years ago, which assumes time-independent couplings. So you create a certain specially designed pattern of couplings given by this expression. So you see that the array is non-homogeneous, non-periodic, and then it appears that you could transfer your excitation from the first to the last side with fidelity equal to 100% perfectly. But there is a problem here that the transfer time now scales with the length of the array as n to the power of 3/2. So very, very, very long transfer time. And this is definitely not optimal strategy as well. So how we are going to seek this time optimal solution? So far, I convinced you that the solution probably exists, but we need to identify it. So, and in this regard, it's useful to employ the concepts of quantum geometry. So we study a projective space where it's like Hilbert space, but you discard the information about the global phase of the wave function. So you are not interested in the global phase anymore. So each point in this space denotes certain state of the system. If we are talking about stationary states, then during the time evolution, as you know, the stationary state only acquires additional phase, e to the minus I omega t. That is why stationary states correspond to the fixed point here, while the velocity of motion in this space is given by the energy uncertainty divided by the Planck's constant. In turn, the line element, so the length between the two adjacent points, is given by the so-called quantum metric, which is a real part of quantum geometric tensor. And so the problem of time-optimal control becomes deeply geometrical in this representation. So we have the initial and final states of the system. So we have these A and B points in our space, and we are interested, and we have some constraints on our Hamiltonian, of course, and we are interested to find a path connecting the 2 points and taking the minimum possible time. It's like finding a geodesic in geometry, but now it's a problem from the domain of quantum mechanics. So we are going to use a sort of variational formulation, and for that purpose we need to write a functional which we are going to minimize. And to simplify our work a little bit, we note that the transfer time here is just from the dimensionality analysis, it's obviously inversely proportional to our constraint on the sum of squares of the couplings and contains some dimensionless function of the array length. So if you want to minimize the transfer time given the sum of squares of the couplings, it's exactly the same as to minimize the sum of squares of the couplings for the fixed time of the transfer, because you have a product of those two quantities. And the latter formulation gives us a bit more flexibility with numerical solution, and this allows me to jump to the following variational form. So we are going to write something like action in the least action principle in theoretical mechanics, but instead of generalized coordinates and generalized momenta, we are going to use such variable as evolution operator. So this matrix U, which depends on t, and which connects the quantum state of the system at the moment of time t and the state of the system at the moment of time 0. If you know the evolution operator, you basically know everything about your quantum system, because from the Schrödinger equation, you could compute the Hamiltonian in this way, which is, I believe, is kind of obvious. And so now we write our cost functional in this form. So this is the quantity we are going to minimize. This is the norm of the Hamiltonian, which is trace of h squared. So if you take our tight binding Hamiltonian and take trace of h squared, you get sum of squares of the couplings. And that's why I'm solving with this constraint, because it's so much simpler than any other type of constraint you could impose. But in principle, we know how to modify this machinery. So we are trying to minimize the sum of squares of the couplings, assuming fixed transfer time, which is set to unity, as I explained to you. And we need to insert in our functional explicitly some constraints which restrict the form of our Hamiltonian, because so far our functional does not know that we are dealing with the tight binding Hamiltonian. And after we specify the form of this
in terms of Hamiltonian.
было очень хорошо.
Okay, so it seems that we disappeared for some moment, but now maybe we need to share a screen, right? Once again.
Difficult to express in terms of Hamiltonian.
No.
Yes.
It was okay,
Just
more or less.
Yes, it is standard.
Yeah, so Mikhail, should we go back a little bit?
But it is standard.
Just 2 minutes, I think it took. No, I think the slide was the same. You explained why J square, why it's, but and then it stopped.
Oh, I see. So how many slides back? So now
It was this slide. The slide, no. The slide was the same. Go to
okay.
11.
11. Okay, perfect. Good. So
Yeah, this one.
perfect. Thank you so much. So I continue from here then, and we'll try to explain that we are using the evolution operator as our generalized variables. Then we express Hamiltonian, and then we were discussing that our constraint in the form of fixed sum of squares of the couplings is incorporated right here. So because this norm of H is nothing but the sum of squares of the couplings with some numerical coefficient like square root of 2 or something. And we need to impose additionally some constraints on the form of the Hamiltonian. So there was a question from Vladimir. Now I'm ready to address it. So you were asking why we are using evolution operator but not Hamiltonian itself. Well, because you could easily express Hamiltonian via evolution operator, but not the other way around. And that's the real issue. Of course, you could write it as a t-ordered exponent, but then you'll have a lot of headache. So that's.
But it doesn't look like equivalent expression for Hamiltonian in terms of evolution operator. And so you say that this is just inverse equation for, I mean, the upper expression, Hamiltonian via evolution operator. But evolution operator via Hamiltonian is t exponent.
Yes.
And how to express, how to inverse this?
Very simple. Yeah, if I understood your question properly, so everybody knows Schrödinger equation, which looks like this. Now you plug in. And now you get this kind of stuff. Yes, sorry to the audience in Zoom because it's.
Oh, I see.
So you do this, and since psi 0 is arbitrary, so you arrive to the conclusion that.
Okay.
And finally, taking into account that U is unitary, so you find that I du over dt U cross is equal to H. And this basically is valid at any moment of time, so it's a universal expression. Very good. So now the key question is how I'm going to impose the constraints. That's the real key question, because if you ignore the constraints and solve everything, then you'll get a very trivial answer. This formalism will tell you that please couple the first qubit and the last qubit directly, wait for some time, and so your excitation will be perfectly transferred. So this is a trivial answer, and that's why it's so important to specify the constraints. So, as I explained already, replying to one of the questions, we are studying the realm of single particle excitations. So, single particle sector of our Hamiltonian. That's why our Hamiltonian is traceless n by n Hermitian matrix. And we request that this n by n matrix includes only nearest neighbor couplings at all times. So, it means that it could only have some non-zero elements at the first codiagonal, and they should be real. No complex couplings, no long-range couplings. Mathematically, this is done by introducing the basis in this space of n by n Hermitian matrices. And so we introduce these generalized Gell-Mann matrices in the following manner. So the matrices which are denoted as AJ, and there are n-1 such matrices, they are responsible for the nearest neighbor couplings, and they could enter into the decomposition of our Hamiltonian. But there is n squared minus n other matrices, which are denoted as Bk, and those B matrices are describing complex couplings and long-range couplings. And we explicitly request that those B matrices should not appear in the expansion of our Hamiltonian. As you typically do when you choose an orthogonal basis in some vector space, we request that our matrices are normalized by these conditions. So you need to choose them sort of orthogonal to each other. And this is standard thing. Gell-Mann matrices do satisfy this condition. And so the constraint which we impose looks like this, very simple. We request that our Hamiltonian is orthogonal to any linear combination, to the linear combination of those Bk matrices. And as typically done when you find conditional extremum of the function, you need to introduce so-called Lagrange multipliers. It's like finding a minimum or maximum of a function of many variables in the presence of several constraints. So besides the couplings, which we didn't know, we get as a gift those additional Lagrange multipliers, which could depend on time, which makes our problem not so trivial, not so easy to solve. So there is a price to pay to find this optimum. So these are Lagrange multipliers, and that's basically our variational formulation. As you see, everything could be expressed here in terms of Lagrange multipliers, unknown couplings, and evolution operator. So evolution operator is our generalized coordinate. And we are gonna to vary with respect to the evolution operator. Luckily, this is done it's not so hard. And then we arrive to the simple and elegant equation, which is known in the literature as quantum brachistochrone equation. So you see that it describes how our Hamiltonian must be varied in time in order to ensure this time-optimal evolution. However, the life is not so simple, mostly because of those Lagrange multipliers. So we had a huge number of them. Here I'm counting the number of variables and the number of equations. So we have how many unknowns? We have n unknown components of the wave function. Now we may forget about the evolution operator. Once we got our quantum brachistochrone equation, we can safely forget about that. So we have unknown components of the wave function. We have n-1 unknown coupling, which we want to find. And we have a lot of unknown Lagrange multipliers, which we are not interested in, but they do appear in our equations. So we have to do something about it. So that's the overall number of variables in our problem. Now, if we start counting, we have enough differential equations. We need to count number of boundary and initial conditions. We have initial conditions for our psi wave function. We can also derive some initial conditions for quantum brachistochrone equation. And that's a non-trivial part, which was first done by us. So previously people knew this equation, but they didn't know the methodology, how you derive those boundary conditions. And you could imagine that it's so hard to solve big system of differential equations without knowing the boundary conditions.
Boundary conditions for what?
So those boundary conditions tell you what should be the couplings in the initial moment of time, what should be the couplings in the final moment of time, what should be the connection between the Lagrange multipliers. And this is sort of not very trivial stuff. Interestingly enough, and what I would like to highlight here, that starting from n equal or larger than 3, the whole system becomes overdetermined. So you have more conditions than you need. This indicates that the solution may not exist. So it may exist or may not, which is understandable. If you impose too many constraints on your Hamiltonian, you will not be able to transfer anything. But luckily, the solution exists and is uniquely constructed. And that's what I'm going to show you. So I was talking about large arrays of qubits, but to get some intuition, let us first look into first non-trivial example, which is an array of just 3 qubits. So it's the simplest system you could imagine. 2 qubits is trivial, so nothing interesting. And we have a constraint. Sum of squares of the 2 couplings is constant. Very good. We do know 2 strategies which bring the excitation from the first to the third qubit. That's stepwise switching of the couplings, which I presented you a couple of slides ago, and constant couplings. So if J1 is equal to J2, and you wait some time, you also transfer the excitation. Both scenarios predict the transfer time equal to pi divided by J0. Now let's see what our methodology tells us about the transfer in this system. So we solve quantum brachistochrone equations, which I showed you just on the previous slide. As anticipated, you get some differential equations for the couplings, but on top of that, you get some Lagrange multipliers. Luckily, some of the equations drop out, and that's why the system of 3 qubits is solvable. So you solve this, and you get elegant and simple answer. So if you want to transfer the excitation from the first to the third qubit, you need to change the first coupling as a cosine function, so it should gradually decrease, and the second coupling should gradually increase as a sine function. So you cannot guess this just from nothing. So there should be some, you need quantum brachistochrone equations to get this result. And then, of course, once you know the form, how the couplings are changing, you could solve Schrödinger equation with those time-varying couplings. And here is the result on the next slide. So if you switch the couplings in a stepwise manner, like panel A on the left-hand side, so then your wave function evolves like this. You have all the maximal population of the first qubit, it gradually decreases, then the excitations are transferred to the second qubit, and then after some time, the population of the third qubit grows, and after time pi, you transfer everything. With constant couplings, the same story, a bit different profile of the wave function, but you still transfer everything within the time pi. However, if you do the optimal control, exactly as suggested here, so cosine and sine functions for the couplings, so this time optimal solution tells you that you transfer actually faster. You could transfer square root of 3 over 2 pi. So roughly speaking, 13% speed up. And that's the best you can get in this 3-qubit system if you constrain the sum of squares of the couplings. There is no way to get faster. So once we got some intuition, please.
The question exactly about intuition. Is there any way to present this, think of this as a motion of this point in the quantum geometrical space, multidimensional? At least for 3 qubits, it could be.
It's possible to present. The only thing is that it's very hard to imagine. You have the constraints on the Hamilton and how they translate into the constraints in that space. There is actually a variational formulation which uses wave functions instead of evolution operator, but it appears to be more cumbersome. Historically, this.
Нет у них этого.
Somehow Zoom is not working. So yesterday I discovered that
it is now. You are back. It was less than a minute. You noticed it immediately. It's fine.
Okay.
You were answering the question from Nalitov.
Okay. Yeah, good. And I do apologize for this.
About wave function representation versus operators.
Yeah. Right. So apologize for this inconvenience. Yesterday I discovered that Google Meet is not working. Today I discovered that Zoom is not working.
Yandex Telemost.
Yeah, maybe Yandex Telemost. So we will have a chance to try this as well. So the formulation with the evolution operator appears to be more useful. Historically, people did this analysis with the wave functions, but there it's more technically demanding. So people know it's known how to do it, but it's more demanding, I would say. Now, after we got some intuition about our
Press on.
Yeah, I need to press click. After we got some intuition about 3 qubits, let's jump to larger systems and see what happens there. So is there any room for improvement for larger arrays? That was the question which we are very much interested in. We spend a lot of time. So we almost instantly solved 3-qubit system. It's kind of simple, but then we spent huge time on understanding large arrays. So here I'm illustrating this physics by a numerical solution for a longer array consisting of 15 qubits. So it tells us that if you want to transfer the excitation from the first qubit to the 15th one, you need to change the couplings in the lattice, but in a very non-trivial way. So So initially you have maximal possible coupling between the first and the second qubit. That's understandable because you need to transfer the excitation from the first qubit elsewhere. Then you gradually decrease the amplitude of this coupling because your resource is constrained, so you cannot afford to keep it as it is. And then you start increasing the second coupling between the second and the third qubit. After some time, you increase the coupling between the third and fourth, and so on and so forth. So you see that it's like not instantaneous, but smooth change of couplings. If we do it properly, then the wave function behaves as this. Initially, we have maximal population of the first qubit. It gradually decreases with time because you switched on the coupling. Then the population of the second qubit starts to grow. Then the population of the third qubit grows, etc., etc. And finally, if you did the protocol of switching the couplings in a proper way, all excitation, the excitation is fully transferred to the last qubit in the array. And my claim is that this is the fastest possible transfer, provided you have this sort of constraint on the sum of squares of the coupling. And interestingly enough, these profiles of the wave function here and here, they're sort of similar up to the shift in time. So this suggests that our excitation travels in the lattice as a localized wave packet. To confirm that expectation, I provide here the results for the same array, 15 qubits, but presented in space-time domain. So this color encodes the square of the respective component of the wave function. You remember that our wave function is a column vector, so it has n intries. And you see that this region where the wave function is non-negligible, it travels with some constant speed given by the red dashed line. So that's our time optimal solution. Green line shows the timing needed for so-called perfect transfer with time-independent couplings. White line shows the result for stepwise switching of the couplings. So you see that all of those protocols are essentially slower than this calculated optimal control. So if you look at a given site and check what is happening there, you will see that the population will grow and then will decrease. So which means that our wave packet passes this site in the lattice. If you look in space domain and fix certain moment of time, we will see that our wave packet is quite closely bound. So just there is some non-zero population just in several sites, and there is nothing in the rest of the lattice. So by doing this kind of analysis, we were able to solve up to 100 qubits and can actually go further. There are some tricks, and we understand that probably we can even analyze the limit of an infinite lattice. This is not done and not published so far, but after some machinery, you could show that the propagation in an infinite lattice should be governed by this kind of equation. So those amplitudes AM, and we sort of need to find the soliton solution of this equation.
This which suggests that there should be some continuous limit, like steps from one side to the other, very small, and then everything becomes continuous.
Yeah, there might be some continuous limit. I do believe that analyzing this sort of limit is better working with this equation. So we were able to show that using the Lux-pair method, it's possible to reduce the whole system of equations we are solving actually to a single differential equation presented on this slide. For those of you who have worked with solitons, and you know that there are solitons in Gross-Pikaevsky equation, so probably you have some experience with that. It's a sort of modification of nonlinear Schrödinger equation, but very strange one, because there is no linear part here. And we were not able to construct a soliton solution so far. But if somebody manages to do so, then they will find a quantum speed limit in a lattice with time varying couplings, and will be able to capture the speed like analytically, not just numerically as we did, but also analytically, because so far we have no analytical solution. And this remains an open problem, which I will be happy to discuss. Yeah, that's a separate interesting story. However, if we jump back to our finite size system, which we are capable to solve, Here I'm presenting a scaling of the transfer time versus the length of the array. So the longer the array is, the more time you need to transfer your excitation. That's absolutely clear. If the couplings are not changing in time, then you're really slow. So your time grows as n to the power of 1.5, so very slow. If we switch in a stepwise manner, then you get this formula. So linear scaling, very good, but it's 39% worse than the optimal control which we computed. So you see we computed all lengths until 20 qubits, but then we were able to, if we are interested in some point, we can extract it. And we are able to recover the result up to 100 qubits. This coefficient here, extracted from our numerical solution, it basically tells you what is the inverse speed of the propagation of the wave packet, and this sets a quantum speed limit in this system with time-varying couplings. Then there are many questions one can ask in connection to these results. For example, how sensitive is the fidelity of the transfer to the disorder in the couplings? Because in a realistic situation, you certainly have some errors. You do not control the couplings perfectly, of course. And then, as you may expect, namely, the fidelity of the transfer decreases when you increase the strength of the disorder. So we do some averaging over 1,000 independent random realizations of disorder, just not to depend on a specific disorder realization. And we see that the scheme with time-independent couplings is very, very sensitive to the disorder compared to our protocol, which is not so sensitive. It's less sensitive to the disorder. But anyways, I cannot claim that this is a maximally robust scheme because we are solving a different problem. And by the way, we neglect the effects of dissipation and loss, as you saw, because we are working with purely Hermitian quantum mechanics, not with Lindblad equations. So these aspects are ignored. And by doing the estimates in our paper, we show that, okay, for superconducting qubits, it's okay to do this sort of assumptions because nowadays they have relatively long coherence times. Of course, compared to the time of transfer between the two qubits. So no special protection against the disorder, unfortunately, but still better than the time-independent couplings. So this actually brings me to my summary. So I'm not going to bother you too much, just a little bit. So our study provides the first example of quantum optimal control calculated for a large-scale quantum system. That's what I boldly wrote in this PRL paper in our cover letter to the editor, and this appeared to be true. So suggested control allows to speed up the excitation transfer, but you could easily imagine that in quantum science you have many other applications, as Alexei asked. In some cases, you need to maybe prepare some Schrödinger cat state. You need to prepare something highly entangled. The same methodology could be applied there. The only change will be in the initial and final conditions which you impose on these quantum Brachistachron equations, and we know how to do it. Well, it will take some time for sure, but we know the recipe how to do it. Maybe it could be also applied to another popular problem nowadays, generation of high harmonics, because you could imagine that jumping between frequency omega to omega 3 omega is like a lattice in the synthetic dimension, and probably this methodology could be instrumental there. Nowadays, there is a huge interest to the topic because of a Wolf Prize and the Nobel Prize awarded for those things. So that's it about this paper, and in the remaining minute I wanted to highlight some interesting connections with quantum geometry. So historically we were working a lot on topological physics, and this topological story is captured by the imaginary part of the so-called quantum geometric tensor. So this is Berry curvature, and it produces a sort of synthetic gauge field in the momentum space. It's responsible for the localized states, as mentioned by Mikhail. It's responsible for the disorder robust transport, and all those stories with which we, and some of you, were playing for many years. However, the quantum geometric tensor also contains the real part, which defines a sort of metric in the real space. The key question is what you consider as these parameters, lambda 1, lambda 2, lambda n. So if you consider the components of the wave vector, then you get some quantity. It's useful in some sort of problems. I believe Dmitry Solnishkov from us, he had a couple of works in that connection. However, another natural choice of the parameter is time. And then this quantum metric, so if you have derivative over time, this captures the effects of non-adiabaticity. And recently this was studied a lot, not only by us. So by chance we were like ahead of time a little bit. And at the end of 2023, when we were actively working on this particular paper, there was an essay paper in Physical Regulators. That's a special format of a paper. It's not like scientific findings, but it's like a perspective of a big scientist, how the field will develop further and what are the suggestions. So Professor Päivi Torma from Finland, not far away from us, where quantum geometry can lead us. And she is explicitly stressing that quantum geometry could play a profound role in many condensed matter systems and probably in those twisted bilayers which are actively studied nowadays, maybe in problems superconductivity at high temperatures, etc., etc. So I'm not qualified to speculate about that, but there is a feeling that this topic is really actively developing, and there could be some interesting findings there in the near future. So among other interesting highlights, as Anton said, introducing me, we are doing a lot of things. So not only this one, but when I'm giving a talk, I prefer to choose one single paper and give you more or less complete understanding of that. And now I spent a few seconds just mentioning other directions. So we are doing nowadays several things on topological photonics, studying the transport in the lattices of in those topological systems. And we are collaborating with a nice experimental group in Chile, in South America, who are fabricating optical waveguides by the direct laser writing. And there we are studying multi-mode waveguides, and the coupling between the modes of different symmetry produces some analog of spin-orbit coupling in condensed matter. So this is a set of nanoletters papers generated by our group and in collaboration with Chile. Another story I'm really excited about is our studies of a special type of non-reciprocal magnetoelectric response in solid-state structures. In that connection, we collaborate with the Nobel laureate, Professor Frank Wilczek, and this story is called axion response. So he predicted long ago hypothetical particles called axions. They are not observed until now, so nobody saw them, even though there are attempts. But it appears that some excitations in condensed matter, namely a special kind of anti-scalar magnons, they feature all the properties of axions. And the electrodynamics of those materials is captured by the equations of axion electrodynamics. So our contribution to this field is twofold. 2 years ago, we were the first to understand the origin of this axion response in metamaterials. And we made an explicit prediction that this response could be stronger by 2 orders of magnitude than in condensed matter. Our prediction, published jointly with Frank Wilczek, initiated like a new scientific direction. Many groups followed that. And actually in 2025, this was shown experimentally, this giant axion response in the experiments of the group of Professor Shang Zhang in Hong Kong. This year, very recently in July, we published a paper in Nature Communications where we predicted a novel type of electromagnetic response, which is similar in many aspects to the axion one, but distinct from it. And that physics is captured by electrodynamics with magnetic charge, which is, I would say, a little bit mind-bending, but as it appears, does not contradict any fundamental principles. So I would say this paper in Nature.com, that's the only one in the history of ITMO University, 120 years, which was published solely by the team from ITMO without any external collaborators. So I'm very much proud about this paper. Well, and of course, I'm happy to have collaborators, but it was that way. And we are actively developing this direction. And I'm very much looking forward to discussions on this topic as well. So with that, I thank you for your attention and we'll be happy to take any questions.
Mm-hmm. So I just want to clarify a little bit the terminology from the point of view of language used by quantum computing community. So this is not a quantum gate.
No, yes, this control we are studying is not a quantum gate. It's just switching of the couplings. That's it.
Yes. So and quantum when you have quantum gates.
You have coherence when you
Yes, surely.
transfer.
Yes,
So
there is no contradiction here.
but this means that it is quantum.
But just by properties, quantum gate is something that transfers any quantum state. You do not do it for some specific quantum state. For any quantum state, it does some operation, transfers it to a different quantum state. Here you consider just one specific quantum state and transfer it. But then you say that it may be extended to entangled states or to Schrödinger case. This I don't understand, because to have an entangled state, you need at least 2 qubits, right? Here you operate with one. You cannot have entanglement in one single qubit.
Yes, absolutely right, but I don't see contradiction. So if you start, let's say, I want to prepare such a state at the final moment of time that I have something in the first qubit and something in the last qubit. And let's say my final state is a null state, which is entangled one. And then how should I switch my couplings in time in order to get this null state? And then by this procedure, we can provide an answer what should be done. But the answer will be different, as you correctly highlighted. Depending on the initial state, you have to switch the couplings a little bit differently.
All right, and for Schrödinger case, because Schrödinger case, you need a many body system, and here you consider every qubit as single particle, right?
Well, if we are talking about Schrödinger cat state, we need to understand, we may start with initializing some superposition in a single qubit and then study how this superposition will propagate. That's also possible. So, well, this machinery allows us to do so.
Okay, so like a very small Schrödinger cat, like single qubit Schrödinger. Because usually when people say Schrödinger cat, it is something that involves at least more than 2 particles.
That's also a legitimate question. Well, let's say we start with this kind of state, and then we see how you can prepare a larger entangled state. So,
okay, thank you.
Please.
The value of the qubit?
With 3, okay, yeah. That's, I believe, very instructive to understand how this system works.
The solution is very beautiful. So the solution for the coupling constant is J0 multiply cosine.
Yeah, cosine and sine functions.
So if you work with a constant coupling, then the wave function will be something like cosine and sine with the time evolution.
Yes.
So
And that's
does this mean some resonance coupling between the neighboring qubit state, and this is the reason why it is the fastest.
Yeah, that's a good question. We were thinking about it in the following way. So as you said, if I take constant couplings, then population changes according to sine and cosine function. So then I move to 3-qubit case. I take sine and cosine functions for the couplings, and then population varies somehow in a more complicated way. And then naively we were hoping that you take a solution for 3 qubits for psi, and then plug it as a couplings for 4 qubits, and then that's it. No, it doesn't work like that. Unfortunately, life appeared to be more complicated. So we spent, I would say, maybe 2 years playing with this quantum register from learning this methodology. So it was not so fast, but then it was fast in parallel.
Another question that you said the constant, which is J square, the summation of the J square is a constant. I'm not very clear about this. So let's say the coupling constant, the Josephson coupling constant, it is average of the overlap act on the kinetic energy, right? So if you write on it in some energy form, then it will be phi star and kinetic energy and phi. So,
Yeah. So if I understood your question properly, so basically everything boils down why we are choosing such form of constraint and what physically it means.
Yeah.
Physically, it means that you have constant energy uncertainty of a system. So delta E. So let's say if you switch off all couplings, then you sort of have eigenstates of isolated qubits. If you switch on the couplings, then and they're time dependent, your system becomes so no stationary states in the system with time varying Hamiltonian.
But if the constant issue will be there's a linear combination and not a square.
Okay. So if I take just a sum of couplings, then there is a simple way to tweak this. You take one coupling positive, one coupling negative. Both of them transfer the excitations, and then you will have no minimal time.
You can say it's all positive.
Yeah. But you know,
the coupling must be positive. No, not necessarily be positive, but actually you can turn it to in order to propagate it.
Yeah. So commenting about the sign of the couplings in tight binding lattices, like in qubits, in waveguides, in coupled waveguide, you could have both positive and negative couplings. Actually,
Yes.
There is a simple procedure how to do it, and in principle, you could also have complex couplings, like in Haldane model with like artificial magnetic field. People can do it, but I'm not speculating about complex here because it will be too much.
I have a question. What is the resulting shape for variation in time of couplings, which gives optimal solution?
For 3 or for 15?
For 15,
for large.
Large, yeah.
Yeah.
But
So
is it Gaussian or?
That's a good question. They're trying to fit by Gaussian, but because if you manage to fit by Gaussian, then we probably find analytical solution. No, it deviates from Gaussian, unfortunately. So somehow resembling Gaussian.
So you don't know.
Yes, we don't have analytical solution. So in case if anybody is working with solitons, is interested in that, we do need some help with this equation. So if you help us to find the soliton solution of this equation, then that will clarify the problem to us. I talked with Alexei Yulin, and he told me immediately that well, there is this kind of system, Ablovitz-Ladik lattice, which is solvable, but this one never seen in the literature. So it's, and I trust his opinion because he's an expert in this physics.
1D, you should not look for Gaussian probably. You should maybe try 1 over cosine, because it is 1D, 1 over cosine hyperbolic in some power.
Yeah, good. Thank you for the suggestion, Mikhail. We were trying inverse hyperbolic cosine, which is a soliton solution of a continuous nonlinear.
In a certain power, not necessarily alone. Plus, there are two parameters, the scale inside cosh and a power of cosh.
Oh, that's very interesting. Maybe we need to try, because we didn't play with the power. It could change the things, yeah. Thank you so much. I will. And then if we guess, then we plug it in here and check that it works or not works.
Since we're on this slide, can you kind of clarify how do you obtain a nonlinear equation from a linear system with constraints?
Yeah, that's a very good question, Anton. So let me explain it briefly. So in fact, we have like a couple of dynamics. We are switching the couplings, and those couplings affect the behavior of the wave function. But optimality condition requires that couplings are somehow connected to the wave function. And then you could imagine that this should bring some nonlinearity effectively, because you have J and psi, you exclude J, you get something nonlinear with respect to psi. Well, a more complex question, so how do I really get this? And what is the meaning of amplitudes A? So previously I didn't have them. And then in the theory of those solitons and nonlinear equations, there is so-called Lux pair method. So essentially it boils down to the following. If your equations are presented in a proper form, and it appears that in our case they're presented in a proper form, you could reduce a complex problem involving both couplings and wave functions to solving a single equation for, how to say, for special amplitude. So these amplitudes, using them, you could express the wave function, and using them, you could express the couplings as well. So you effectively kind of reduce your problem. But the real issue here is that you could solve this equation numerically, no problem here, but finding solitons is a daunting task.
Okay,
It should exist here, but we don't know.
okay, so if it is a soliton, then what would be the continuous variant of this equation?
Continuous variant will be the following. We say that AM corresponds to some function, I don't know, y, which depends on x, and AM minus 1 and AM plus 1 should be like Taylor expanded. It is still not clear whether continuous version provides any soliton or we should keep discrete versions. It still remains to be understood.
Okay.
Then you can make a Fourier transform to this. So you can assume m equals to some exponential I and multiply some best.
Well, we probably have this exponential, but we also have this, you see, wave packet.
Yeah, that doesn't fit.
Yeah, unfortunately, with nonlinear stories, it's a bit harder than that. Please.
For n equals 15, the width of those packets that are traveling is only 3 qubits, so it's quite discrete here. As you increase n to be larger, do these packets also become wider?
No. The width of the wave packet remains fixed, and the only modification, only change happens here around the edges of our structure, because you see that initially you have just a single photon in the first qubit, then this distribution had to transform into a wave packet, then this wave packet propagates, and then at the end of the array, it transforms back to a single excitation.
And then if there is, for arbitrarily large n, there is always, the width is always roughly 3, and there is always a large variation between adjacent sides. So
yes.
Continuous version of the equation wouldn't be related to.
Yeah. Very good observation. That's why we were pessimistic about continuous version, but well, naively you say maybe we cannot expand in Taylor series, but maybe you can. I don't know. So we don't have a definite answer.
You have ES3 just because you have on the nearest neighbor coupling.
Yeah.
You have more coupling, spread of wave function.
Yeah, that's absolutely right, but that's becomes a separate problem, because then you have to to manage this a bit.
Any more questions from the Zoom?
Yeah, sorry for this poor connection.
It was okay. I think I asked everything. So dissipation is kind of slower than interbit connections. So you kind of completely ignore dissipation.
Yes.
How are you going to read out? Because, or come in? It's kind of a little bit scary. Because if it is totally closed system, how do you induce it with a particular starting state?
Good. I understood your question. So let me briefly comment. So if we are talking about superconducting architecture, it works like this. They can control any qubit in the array, and they have this control via so-called dispersive coupling. This dispersive coupling has a nice feature. So if you read out the number of excitations, it still remains the same. So sort of non-destructive quantum measurement, which is guaranteed by the fact that the Hamiltonian of the dispersive coupling commutes with the number of excitations. Now, in superconducting architecture, possible experiment could look like this. They apply pi or pi over 2 pulse to the first qubit, so they rotate it to the excited state. Then they start playing with the couplings. And then at the end of the day, they wait for some time, and then they apply readout to the last qubit. And then they detect. So in principle, if the dissipation is slow enough, as you highlighted, then this strategy should work. So there shouldn't be any conceptual problems here.
Okay, thank you.
And if there is no more questions, then let's thank the speaker again.
So the next time, what will be the next speaker? Daniel will. So next Wednesday, we have Daniel. Yeah?
До свидания.
У вас уже какие-то